In this lecture, we will learn about oxidative phosphorylation that is happening in complex 5 of electron transport chain. The free energy released by electron transport must be conserved in a form that ATP synthase can utilize it, which is referred to as energy coupling or energy transduction. Oxidative phosphorylation requires an intact inner mitochondrial membrane which is impermeable to ions such as H plus, OH minus, K plus, Cl minus, whose free diffusion would discharge an electrochemical gradient. Compounds that increase the permeability of the inner mitochondrial membrane to protons dissipate the electrochemical gradient but inhibit ATP synthesis. Conversely, increasing the acidity outside the inner mitochondrial membrane stimulates ATP synthesis. Thus, sequestered free energy by the resulting electrochemical gradient is called proton motive force (PMF), which powers ATP synthesis. Proton pumping is an endergonic process. Approximately 2.5 protons are passed back into the matrix from the intermembrane space. The protons which are released during the electron transport chain are again passed through the ATP synthase back into the mitochondrial matrix. Thus, passed protons form one ATP from 2.5 H plus ions. Two mechanisms are involved in coupling the free energy of the electron transport: the redox loop mechanism and the proton pump mechanism, which we will see in detail. Redox loop mechanism generates proton motive force by coupling electron transport with protons translocation across the membrane, thereby creating an electrochemical gradient for ATP synthesis. Whereas proton pump mechanism pumps protons across the membranes against their concentration gradient. Now let us see the mechanism of ATP synthesis. The free energy of the electrochemical proton gradient across the mitochondrial membrane is achieved through the synthesis of ATP by proton translocating ATP synthase or F0 F1 ATPase or complex pi or F-type H plus ATPase. ATP synthase consists of two major substructures comprising 8 to 13 different subunits. Ephraim Racker discovered ATP synthase, which comprises of two functional subunits F0 and F1. F0 is a water-insoluble transmembrane protein composed of as many as 8 different types of subunits that contain a proton translocation channel. F1 is a water-soluble peripheral membrane protein composed of 5 types of subunits. With the treatment of urea, F0 and F1 subunits can be dissociated. The F1 subunit of the mitochondrial F1 F0 ATPase is an alpha 3, beta 3, gamma, delta, epsilon nanomer, in which the beta subunit contains the catalytic site for ATP synthesis, and the delta subunit is required for the binding of the F1 F0 subunits. Electron micrographs of F1 F0 particles from E. coli show that there is a double dumbbell shaped structure in which the F0 and F1 are joined by a long central stack and a less substantial peripherally located connector. The F0 component of ATPase from E. coli consists of 3 transmembrane subunits A, B, and C. The hydrophobic C subunit of F0 forms a ring with A and B subunits. The C subunit consists of two alpha helices that are connected by a 4 residue polar loop and that are arranged in a banana shaped antiparallel coil. In the F1 F0 ATPase, the rotor is proposed to be an assembly of the C ring with the gamma and delta subunits. This is known as the rotor. Delta subunit together with alpha 3 beta 3 delta subunit together with alpha 3 beta 3 form the stator. The rotation of the C ring in the membrane relative to the stationary subunit is driven by the migration of protons from the outside to the inside, that is the mitochondrial matrix. The B2 delta assembly presumably functions to hold the alpha 3 beta 3 spheroid in position while the gamma subunit rotates inside. Now let us discuss the binding change mechanism, that is the proton translocating ATP synthase is driven by conformational changes. The mechanism of ATP synthase can be studied in three phases: translocation of protons carried out by F0, and the second one catalysis of formation of the phosphoanhydride bond of ATP carried out by F1, coupling of the dissipation of the proton gradient with ATP synthesis, which requires interaction of F1 and F0. The conformational changes in the ATP synthase in a transverse section can be studied here in this diagram. The conformational changes in the ATP synthase that power ATP formation are generated by proton translocation rather than by direct electron transfer. F1 is proposed to have three interacting catalytic protomers, each in a different conformational state, L, T and O. O is the open phase, L is the loose phase and T is the tight phase. F1 is proposed to have three interacting catalytic promoters, and the free energy released on proton translocation is utilized to interconvert between these three states. The phosphoanhydride bond of ATP is synthesized only in the T state and the ATP is released only in the O state. O is the open state. The free energy released on proton translocation is utilized to interconvert between these three states. The phosphoanhydride bond of ATP is synthesized only in the T state and ATP is released only in the O state. Initially, the ATP formed is attached to the T state of the F1 particle of the ATP synthase. Thereby, then again ADP plus PI comes and binds with the loose state of the ATP synthase, which releases ATP outside through O state. O state is the open state where the ATP synthesized is moved into the matrix. This cycle of ATP synthesis continues as far as there is a proton pump inside the ATP synthase of the mitochondrial inner membrane. Thank you.